in this beam, whenever a load is being applied, for example, that load is P. Now what happens to that load? That load is stored within the element itself as a strain energy. A strain energy is always a potential energy. So strain energy that we are talking about, it's a potential energy. Now, how is it stored? Whenever the element undergoes certain amount of strain, that strain is that leads to the development of the potential energy within the element. So for every work done, for every load that's transferred, this is the load that's transferred, load P, there will be a complementary strain energy which is stored within the system. So work done is always, it will be equal to the energy stored in the system. Now that energy is mostly stored as strain energy. So there will be a relationship between strain energy and the work done. Then there is another relationship between the, what also happens when you have a load, what will also happen is that this will undergo deformation. Now there will be slope at the end of this. There will be a slope at the end. That slope you can measure here. There is a slope here. Then there is a slope at this end. And so you have slopes at the two ends. Then you also have deflection, which is happening at the center of this. Now this is the amount of deflection that has happened in the element here. So along with strain, you also have, along with the development of strain energy, you also have deflections as well as slope in the element. So there is a relationship then between strain energy and deflections as well as slope. There is a relationship between strain energy and deflection as well as between strain energy and slope. So you can determine those relationships, and that we'll do during the course of this lecture. So first thing, what we need to determine is the elastic strain energy. How do we determine the strain energy? So the first term that we had to discuss is the elastic strain energy. Now what is elastic strain energy? Whenever I told you we apply the load, we have the strain developing in the system. Now the work done is stored as strain in the strained member. Now there will be an expression that we have to determine for various types of strain energies. Now what are the various types of strain energies that can be stored? First condition is the development of direct tensile or compressive strains. Now, if we have a member, for example, this is a member column. Now in this column, if this column is of length, अगर इसकी length हमारे पास जो है, if this is L, say this is L, then we have the area of cross section of this column is A. The area of cross section of this column is A. we then have, for example, under the load P, if there is a load P acting somewhere here on this column, there is a load P acting on this column, then what will be the extension in the length under the load P? There will be a deflection, there will be a strain happening. So there will be extension of this column. Now this much extension that is happening due to load in this column, for example, if that is dx, if the extension in the length is dx, in the length dx, what will be that extension? Or we can say it's we can take this in this manner, that let's take an element portion dx of this column. Now what will be the extension in dx portion of the column? The extension will be, for example, if that is delta, that is delta L, which is the small incremental uh, uh, deflection or the extension in the length, in the portion of, it will be P into dx divided by A into E, because we know P is equal to AEL by dx. Thereby, if we have to determine the total deflection, the total deflection would be, or extension would be, of the whole member. ये सिर्फ dx portion का है, delta L. The total extension would be, for that you have to do the integration. If you want to determine for the whole member, that will be the same delta this one, but you will have an integral you will have an integration so this is integration of P dx. Now integration would be from 0 to L. That would be the value of integration here. 0, it will be from 0 to L. So this will be the total extension. Now because the force P will not be acting, so ये एक साथ act नहीं करेगा, it will start from 0. So actually the force is acting like this. It's starting from 0 and then it goes to load P. So if we at least take the average of this, you will have at least load P by 2 acting over it. So we can take the average force. Average force is P by 2, which under which this is getting displaced, or extension is coming to be delta L. So the actual work done would be, how do we define work done? We define it by U. So U is the work done, would be equal to its load. How much is the load? P by 2, which is the average load, into extension. Extension is delta into L. This is the P by 2 into delta L. So you actually have overall U then equal to, which is equal to half times P and delta L. So it's P by 2. What's delta L? If we take from this relationship, delta L is this. This is the value of into delta L. So this is uh, what you are actually getting. U is equal to this. Thereby, if the value, the area of the section, area of the cross section, A, if that is uniform, what we finally get is, if we integrate it, we get U is equal to P square. This is actually square at the top. This is P square. It's at the top into, you have divided by E into L. So you have, or you can say P square L by EA. There will be also 2 at the bottom, 2EA. So this is the equation for U. It is U equal to square of P into L divided by 2AE. So now if we know that what is the P by A. What is P by A? It's stress. Stress F is P by A. So then you have the value of U equal to, you can say it's F, square of F divided by 2E into AL. अगर आप इस equation में, if you put replacing P by A with F, then this is what you get. So you actually have this equal to F square of F divided by 2E into volume of member. It's into volume of the member, because the volume of the member is A into L. So thereby we can say that U is actually equal to square of F by 2E into volume of the member. So that's the strain energy which is stored. This is the strain energy which is actually stored under direct tensile or compressive strains. So under direct tensile and compressive strains, strain energy is F square by 2E into volume of the member. Then there may be bending strain. Now the second case is the bending strain. Now in the bending strain, I'll just write down the overall, I will not be deriving this. The overall equation would be, for strain is M square of M divided by 2EI into ds. So this, there will be an integral here. This is square of M square by 2EI into ds over a distance, a small incremental distance of ds for any member which is in bending strain, So it will be a member actually which will be a beam, for example, which is under bending, and you take an incremental portion of this beam, this much portion of this beam of length. This portion will have length ds, and the moments that are generated in this beam are m, and E is the modulus of elasticity of this beam. So you will have to remember this. These strain in the actual member is square of P by PL into 2AE, and for bending strain, it is m square by 2 EI into ds. Similarly, you can have for shear and torsion, and that will not touch here. Then where is this applied? What's the application of these formula? Let us move into the application part. So if you have, for example, a cantilever, you have a cantilever. Now, if you want to determine the deflection of this cantilever here, you want to determine the deflection at this position. Now, the deflection would be happening under certain load, and let the deflection be measured. For example, if this point is A point, and this point is B, if the length of this member is L, if the length of this member is L, now what would be the deflection that would occur at this point B? That's what we have to determine. For example, if that deflection is any value delta, for example, it's delta here, the deflection here, that we have to measure at this point. So it would be, for example, it's delta B. We are terming it as delta B. What is the amount of deflection that's happening at point A? This is fixed. What's the deflection that's happening here? Deflection here, 0. So this is 0. We have to measure the deflection at point B. So what do we do? The bending moment, we had to first determine the bending moment at any section. Let that section be X section, and this section is at a distance of X. It's at a distance of X from this end. It's at a distance of X from this end. Now, there is a small section that we are incrementally measuring here, and this section here is it is delta X. This is delta X. Now, the bending moment at any section here would be, what is bending moment here? At any section X would be the load.
X.
Now, how much is the load? If the load is acting somewhere here, the load is acting at the end. This load is acting at the end. This one is acting at the end. And if this load is, for example, W, so bending moment would be W into X at section X. So bending moment at section X is W into X. Thereby, here in this example, we have ds, जो हमने अभी इक्वेशन लिखी, वहां पर हमने ds मेंशन किया फॉर एनी बेंडिंग मोमेंट सेक्शन. It's actually equal to delta into X. Thereafter, what we have is, what is then the value of strain energy? What is the value of strain energy? It's U. अभी हमें क्या निकला वहां से? Let's recall that equation. U is this. So this is the value of U, m square by 2 EI ds. Now what is m here? It's delta. So this equation would become, this would become equal to it would be square of W into X. M is W into X. So it's square of W into X. Then you have ds is dx, और पहले हम नीचे के terms will mention. It's dx divided by 2ei. Now this is integrated from 0 to L. So the overall equation would then turn out to be, अगर आप इसकी इंटीग्रेशन करोगे, it will be square of W into cube of L cube है, divided by 6ei. You have to integrate this over dx. जब आप इसको इंटीग्रेट करोगे, what you will actually get is W into x square by 2, but this is, then it will be again into W into x by 2, x by 3. So overall you will get W square L cube by 6ei. So what is the amount of work done? Work done is, this is strain energy which is stored. We already know, we have just seen work done is W into, the average work done is actually equal to W into जो हमने अभी निकाला,
W by 2 delta L.
हाँ, into 2 delta L. So this is the work done. So we can write it down. It's into W by 2 into L. It's W. So, but you have to also take into care that you are determining the work done is at the end of this. So W into delta B is the work done. The amount of deflection that's actually occurring due to this work done. So the work done is W into delta B, and because we are averaging it out, it's then divided by 2. So this will be equal to what we have just got, this W square L cube by 6ei. Thereby, what we have to actually determine is delta B. We have to actually determine the value of this. Delta B will then be equal to, it's again square of W. तो वहाँ से क्या बचेगा? It will be just W into L cube by, now what will remain is just then, जब 2,
3ei.
it will be 3ei. So it will be W into L cube. So it will be cube of L divided by 3ei. That's what we are getting. So the deflection for the cantilever at this end, from strain energy method, we have got this is W into L cube by 3ei. Similarly, you can take another example which you will do yourself. This is a simply supported beam. You will have to do this question yourself, and we are applying a load W, at a distance of A from one end and B from the other end, and it's at a distance of B from the other end. The overall length is, L. This overall length is L. So solve this question yourselves at your own place. This is a simply supported beam wherein you have to now determine the deflection. Now, where would you be determining the deflection? If this is point A, if this is point B, and if under the load W there is point C, so you would be determining the deflection at the point C, not B, C. You will be determining the deflection here, delta C, under this load. This is the question that you will be doing yourself. Then we would move to the next question. We can also determine the slope of any beam. We can solve that question as well. First, I'll end this session, then we'll join again.